Okay, here's a quick video over sections in Chapter 4. 4.2 is just dimensional analysis again. So for example, if you want to go, say, from 45 miles per hour to maybe centimeters per second, you would use dimensional analysis. So remember, when you have a rate, you have numbers both places, so miles per hour. And then you just pick one that you want to cancel first, so maybe miles. So miles are on top, so I need miles on bottom. And I know that there's 5,280 feet in 1 mile. And again, this has to be a 1-to-1 ratio. So then I'm in feet. So then from feet, I need to get to inches. So feet and inches. And again, these need to be top to bottom. And I know there's 12 inches in 1 foot. So again, that equals 1. And now I'm in inches, and I need centimeters. So inches on bottom, centimeters. And I need to know that there's 2.54 centimeters in 1 inch. These cancel. And so now the centimeters part is good. I'm done on that kind of frame. But now I got to go back here and get hours. So I'm going to make that a little smaller here. So maybe, I don't know how many I'm going to need, but I'll make it a little smaller just in case. So let's see. I have hours, so I'm going to put hours on top. And 1 hour has, what, 60 minutes? And again, these better equal 1. So now hours cancel. 60 minutes. Minutes is on bottom, so I need minutes on top. And so I know that 1 minute has 60 seconds. And so I have another unit I want as seconds. So I don't need that last little container thingy. All right, so everything on top gets multiplied. Everything on bottom gets multiplied, and then you divide. So you're going to take whatever answer you get in the numerator. You're going to divide by whatever answer you get in the denominator, which in this case is what, 3,600, I guess. So multiply this times this times this times this, and 1 and 1 aren't going to do anything. Take that answer and then divide by the 3,600 you get here, and then that would be your centimeters per second. The only new thing in this section, so this should be review, the only new thing is that we never did like square inches and things like that. So say you want to buy carpet and you know that you need to buy 40 square yards. But a lot of times in carpet places, they sell it by the square foot. There's not 3 feet in a square yard. A square yard is a yard by a yard. So that's 3 feet by 3 feet. So there's actually 9 square feet in a square yard. So the easy way to do this when you have units that are squared is just write it twice. You only have the number 40, but your unit is squared, not the 40. So then what you can do is do dimensional analysis with that. Just do it twice. So this yard is on top, so put yard on bottom. And there's 3 feet in that yard, so I canceled one of my yards. And then yards on top, so yards on bottom, and there's 3 feet in that yard. And notice that that will give you the 9 square feet that are really in a square yard. So then you just multiply across. So what is that? 360 square feet that you would need to buy to be the equivalent of 40 square yards. And so with those square ones, it's just easier to write it twice. You need to be careful with a square foot as well, because if it's a foot by a foot, that's really 12 inches by 12 inches. So there's actually, if I don't know, if I drew in all the squares, there's 144 square inches in a square foot. So again, if I was going to do some type of dimensional analysis and I was converting square feet to square inches, I would just like, if I had 4 square feet, I would just write it twice, feet, feet. And again, just the unit is squared, not the 4. Right? And then, so I'd be like, okay, I need to cancel feet twice. So I'm going to put a foot and a foot on bottom. And I know 1 foot has 12 inches and another foot has 12 inches. Notice both feet cancel because I have 2 of them. So then I take 144 times 4 and figure it out. So take 4 times 12 times 12, and then that would be your answer in square inches. All right, so that's kind of a nutshell of 4.2. Let's look at 4.3 and 4.4. I kind of think the book teaches these in the wrong order. So if we look at 4.3 and 4.4, The main thing I want you to know about 4.4 is that negative exponents just mean to reciprocate. So if you know that like 4 squared is 16, negative exponents just mean it's in the denominator. All right, it doesn't mean you owe money. If I owed money, I'd put it out front, like I owe 16. This is an exponent. So what it really means is just square it like normal, which is 16, but then flip it, reciprocate it. So negative exponents really just mean reciprocals. So like x to the negative second just means x squared, but it's been flipped. It's on the denominator. It's on the bottom. So in a sense, it's kind of like you're dividing by that. If you know 5 cubed is 125, then you know 5 to the negative cube would just be, again, the reciprocal of that. Just flip it over. Okay, that's all negative exponents mean. And notice, like, remember when we subtracted exponents, we never did a certain type on purpose, but you can kind of see it now. So if I had x squared over x to the fourth, notice if you cancel them, because the trick is to subtract, right? Cancel, cancel. You would get 1 over x squared, because you'd have more x's on bottom left over than our top. But notice the whole, when you divide, you subtract. So 2 minus 4 is a negative 2. So technically, if I use the subtraction thing, I'm going to get x to the negative 2. But again, negative exponents just mean to flip. So they're just the reciprocal. And once you flip it, the negative's gone, because that's what the negative means to do. So if you have like x to the negative third, you flip that part. Okay. If you have something like part of it's negative and part of it's not, so say I give you something like, oh, I don't know, like x squared y to the negative third, this is fine. It doesn't have a negative exponent, but the thing that's getting flipped is that guy, that reciprocal. All right, so now I want to look at the last thing, which is scientific notation. And so with scientific notation, it's how we write really big numbers or really tiny numbers. So if I give you like 3.6 times 10 to the fourth, that means you're going to multiply by 10 to the fourth 4 times. So if you think about what that means, if you multiply it 4 times, it's going to get bigger. So we're just going to end up moving the decimal. So let's see, the decimal's here, 1, 2, 3, 4. So it'd be 36,000. This is called standard form. This is called scientific notation. If I do something like 3.08 times 10 to the negative fourth, okay, again, think about what negative exponent means. It really means that you have 10 to the fourth down here. So in a sense, it's like you are dividing by 10 4 times. You're not multiplying by 10, you're actually dividing. So think about what happens when you divide by 10. You move the decimal and it gets smaller. So if you have a negative exponent, you're really dividing by 10. So you're going to go 1 jump, 2 jumps, 3 jumps, 4 jumps. So that answer would be that. So negative exponents are tiny things, less than 1. Positive exponents are things that are bigger than 1. And so we use scientific notation for really big things and really tiny things, just so that we don't lose some zeros. So if I give you something like this, right, in a journal article or something like that, if we're talking about science, it could be really easy to just leave off a set of 3 zeros. So instead, we take the significant digits. Oops, didn't mean to grab that. So the number is up here, and it has to be between 1 and 9.9. So basically, you take the important digits and you always put the decimal after the first place value. So it's always between 1 and 9.99999. So always after the first spot. And then you're going to do a power of 10. So times 10, because 10 is what moves the decimal. So this is a really big number, so you're going to have a positive exponent. So how many jumps does it take for the decimal to get here? Well, the decimal starts at the end of the number. So it's there. So there's 3, 6, 9, 12, 13, 14, 15, 16 jumps. So the exponent's 16. And it's positive because this is a really big positive number. And if you want to check your answer, take this times 10, 16 times, right? And then it should equal that really big number. Same thing if you have a really, really tiny number. Again, it's easy to leave off zeros. So in science, that's a problem, especially with really like microscopic things. So it's like, if I was typing this, if I left off a 0, I probably wouldn't even notice. So scientific notation is a little safer. So find your significant digits, and if there's zeros trapped in there, these are significant. So I have 8006. You always put the decimal after the first digit. So this has to be between 1 and 9 point blah, blah, blah. Times, and then the 10 is what moves the decimal, because these have to be equal to each other. It's not like we're rounding or anything. We're not rounding. We're just, you know, writing it in a more concise form. So you're going to count jumps to get the decimal from where it is, which is here, to here. So count jumps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now, it's a negative 13 because this is a really tiny number. Oopsie, I'm not sure what happened there. There we go. This is a really tiny number. And so to check your answer, you would take 8.006. And remember, negative exponents mean they're down here. It's really division. So if you take 8.06 and you divide it by 10 13 times, right, would it give you this tiny number? And the answer is yes. Okay. So scientific notation is how we write big numbers, small numbers. Sometimes we use it in science to write significant digits, so it's not like the numbers are really that big, but we're just trying to tell people where we rounded to. So in your book, why don't you turn to page, why don't you try number 3 on page 468 and number 4 on page 469 and number 5 on page 470. So 3, 4, and 5 starting on page 468. Okay, so the requirement for scientific notation is you have a digit in front of the decimal and some other stuff. So this is between 1 and 9 point something times 10 to some power. This is yes because it fits the requirement. You can have negative. This is no because, well, you don't have either part. This is a no because this is fine. The problem is this is bigger. So it should be 7.9 times 10 to a different power, like a negative 3. This one has the part, this part, but again, this should be 9 times 10 to say the 11th, right? Like 9 point. It has to be above, between 1 and 9. This one looks good. Anything to 0 power is 1, but that's totally fine. This, you can't have 2.3 jumps, because remember your power of 10 is how many times you're multiplying and dividing. So this exponent up here always has to be a whole number, so a decimal wouldn't make sense, so this is a no. And then this last one looks good, so that's a yes. All right, pause, and if you haven't done number 4 yet, do that quick, and then we'll come back there. Okay, so here we're undoing scientific notation to get standard. So you have 9.62. You're multiplying by 10 to the 6, so that's going to make it bigger. So 1 jump, 2 jumps, 3 jumps, 4 jumps, 5 jumps, 6 jumps. So if I put my commas in there, what's that going to be? So what, 9,620,000? Oopsie, my pen's not working very good. Okay, for some reason it does not want to write over there. Okay, let's try 9,620,000. Okay, and it makes sense that it's bigger because I am multiplying by 10, 6 times. So you're really multiplying by 10 over and over. And when you multiply by 10, you can just move the decimal. And then this one, it is a negative exponent, which means you are dividing by 10 because negative exponents mean to reciprocate. So you're really dividing by 10 6 times, which should make it get smaller. So I'm going to take my decimal and I'm going to move it this way. So 1, 2, 3, 4, 5, 6. So it should be what, 0.0, what is that, 4 zeros, 5 zeros? Okay, and it makes sense, again, that this one's getting bigger because it has a positive exponent, so you're multiplying by 10 all the time, and it makes sense that this one got tinier because if you take 9.62 and divide by 10 over and over again, you're going to get this number right there. All right, go to number 5. Okay, to write in scientific notation, you always put the decimal after the first digit, and then you have to multiply it by a power of 10 because these have to equal. So how many jumps did I go? 1, 2, 3 jumps. Decimal's at the end, and I'm moving it right there. So it's 3 jumps. And it's a positive 3 because this is a big number. And I would have to take this decimal times 10 3 times to equal up to 5,000, because one 10 would move it once, the other 10 would move it again, and the other 10. So for it to be equal, I need to multiply by 10 3 times, so positive exponent. This one, I need to put my decimal after the first digit, so right there.